Good morning, guys. Today we are going to be starting chapter 12. With chapter 12, we're adding a couple sections that we did last week from section 10.6, and that was on arc measure and arc length. Today we're going to do a little section on tangents. Okay, so you need this tip chart. You need the 12-1 notes on tangents of circles, and now we're going to get started. All right, so you've heard the word tangent before when we were talking about right triangles in chapter 8, where we did the trig ratios, sine, cosine, and tangent. This topic, tangent of a circle, is related to that one out there in the wonderful world of calculus, so we're not going to get into that. It'll seem to you right now like it's just a completely disconnected topic, but they are connected out there. All right, so the word tangent. A tangent of a circle is a line. So write down, it's a line. And it's a line that touches a circle or intersects a circle in exactly one point. A line that intersects a circle in exactly one point. Now, I don't know if I've mentioned it before, but when I write the word circle, I put like just an O, but I put a dot in it. And the reason I put a dot in it is because if you don't, sometimes when you name like circle C or circle A, it'll look like you're writing OC or OA. So that's why we put a little dot in the circle symbol. Okay, so I want you to think about that and see if you can imagine that. Can you imagine a line that is only touching a circle in one point? So I want you to see if you can imagine that. I have misplaced my circle maker, y'all. Okay, so I guess a question that I would ask in class is, could that line be passing through the circle? If it's only touching it at one spot, could it be passing through it? So hopefully you're thinking about that. And the answer is no, it could not be going through it. Because if it were, it would have 2 points, an entry point and an exit point. And it's only touching it one time. So here's what's happening. The line is just kind of grazing the circle. So draw a circle. Actually, I think I may have drawn one for you. And a tangent line is just grazing the circle, just leaning against it like that, and it intersects it at just one point. So that right there is a tangent. Now, since it's a line, you name it like a line. So you either put a lowercase cursive letter towards one, we say end of the line. Lines don't really have an end, but the way we draw them, we have the arrows there. So you could call it line L, or some people will pick out any other point on the line, and remember there are infinitely many of them, and they might name it line AB. So you name it just like you name lines in other contexts. You could say line AB is tangent to the circle, or you could say line L is tangent to the circle. All right, that's all there is to tangent. I put it a bullet point like I was going to put something else, but that's all I'm going to put there. A line that intersects a circle in exactly one point. Okay, now you'll notice that creates this, or that points out this one point, right? If you've got a tangent, then you've got one point to be concentrating on, and they call that the point of tangency. So the point of tangency is the point of intersection. It's that point of intersection, that exactly one point. It's the point of intersection of a circle and a tangent. So since a tangent intersects a circle at exactly one point, there's a point of intersection of that circle and that tangent line. So I have a circle here for you. I'm going to draw a different tangent. That point right there is called the point of tangency. Point of tangency. Okay, and those are the two that we need today, a tangent line and a point of tangency. Just hoping you guys can see all that. Okay, so now we need these notes paper. All right, so today we're finding out what happens at this point of tangency. Okay, so here's a theorem. There's one theorem, I lied, there's two theorems today. Okay, so the first theorem says, if a radius is drawn to a point of tangency. So in this picture, we have a circle, we have a tangent line. If a radius, and remember there's infinitely many radii, you could put a radius anywhere in the circle. If you draw it to that particular point of tangency, like that, then something happens, okay? So if you draw a radius to a point of tangency, then it, meaning that radius, is perpendicular to the tangent. So anytime you draw a radius to a point of tangency, to a tangent line at that point of tangency, you're gonna get right angles. So they will not, the hard part is they're not marked for you. They will not be marked for you. So that is a right angle, that is a right angle according to this theorem. Okay, so now we're going to use that in some examples. Example 1. So in example 1, they want us to find this angle down here. I'm going to put a little degree mark. They want that angle. And we've got a radius, and that radius is going to a point that's connected to part of a tangent. So sometimes you won't see the whole tangent line, but remember, a segment's part of a line, so there's a tangent line there. And so since this radius is intersecting that tangent, that's called a point of tangency, and according to this theorem, that's going to be a right angle. And then it happened again down here. So that radius is drawn to this point of tangency. There's our tangent line. It's just part of it. And so we've got a right angle there. Now, if you were to take something and measure that angle, I drew this on a in Word a long time ago, and I think my tangent line might be off a little bit. It might be leaning a little too much, so you may find out that that's not actually a right angle because of my terrible drawing. But in reality, if that's a tangent line and that's a radius going to it, that will be a right angle. All right, so now there's a couple ways you can solve this for x. A couple different rules you could use. So one rule is that the four angles in any quadrilateral will add up to be 360. That's probably the easiest thing to do here. So you can take 360 and you can take out the 90, the 120, and the 90. And when you add up 90 and 120 and 90, you get 300. And so you can take that out of the 360, and that leaves 60 degrees. That's probably the easiest thing to do. So x is 60 degrees. There's other things you could do. You could draw this line going down the middle. Anytime you add a line to a drawing, remember that's called drawing in an auxiliary line. And it would bisect the 120, and then you could use the triangle to get just half of that angle. The only problem with that is some people will find this and then they'll forget that it's both of them that make up x. So I try not to do things like that I would tend to forget later. So that's how I do this one. Okay, example 2. So we have this, now a lot of times they're going to be tangent segments. So we have this segment here that's grazing the circle, right? This is just touching at that point. So that means it's a point of tangency. This is our tangent line. And that C means it's the center of the circle. We try to call that point C. A lot of times they'll call it point O for some reason. Maybe because circles are placed at the origin a lot. But anyway, so that, since it's a diameter, we've got ourselves a radius right here. And that radius drawn to this point of tangency is making a right angle right here. And now we can use this right triangle to find out what x is. X is this angle. This time we have a triangle and not a quadrilateral. And you guys have known for a long time, since chapter 3 at least, but probably way earlier than that, earlier grades, that the three angles add up to be 180. So you take 180 and you take out 90 and 42, which is 132. So that's 90 and 42. And when you take that out of 180, you get 48. So x is, my 4 looks crazy. X is 48 degrees. X up here was 60 degrees. Okay, example 3. So example 3, same kind of drawing. We've got this segment right here that's grazing the circle. So we've got ourselves a point of tangency. And here's a radius drawn to that point of tangency. So we've got ourselves a right angle. And this time, x is a segment and not an angle. So be careful about that. These are all angles. These are angles. These are segments. All right, so since it's a right triangle, to find a missing segment, which is this, I would like to use Pythagorean theorem. But we've got some things missing, so we need to think about that. Okay, so in this picture, this is a radius, and that radius is x. Well, in a circle, every single radius you draw is going to be x in this circle. And so we see another radius right here. So that means this radius is also x. Now, I have had some instances where kids thought that 8 was referring to that whole line, but it would not be possible for that whole line to be 8, because in a right triangle, if this leg is 12 and the hypotenuse is always longer than the 2 legs, well, that's not possible for that whole hypotenuse to be 8 then. So, so that 8, that's how I knew it was only referring to this little piece. Plus it's drawn out there, so that would be very deceiving if they wanted it to be the whole thing. All right, so now we've got at least names for all the sides of the triangle. And so now I'm going to do the Pythagorean theorem to solve this thing. So remember, Pythagorean theorem is a squared plus b squared equals c squared, and it's used to find missing sides of right triangles when we know the sides, or when the sides are labeled. X squared plus 12 squared equals, now this part's a little bit tricky. It's x plus 8 squared. Okay, now we got to solve this thing. So x squared just stays x squared. 12 squared is 144. This right here, it's been a little while since you were in an algebra class. This is not x squared plus 64. See, some people think they can just square the x and square the 8, but you cannot do that. This means right here, I'm going to write it over here, this means x plus 8 times x plus 8. That's what that means. So to multiply that or to square that, you have to FOIL it. So this is good practice because next year you're going to be doing quite a bit of this kind of algebra. All right, so x times x, that's x squared. X times 8 is 8x. All I'm doing is distributing. I distributed the x, and now I'm distributing the 8. 8 times x is 8x, and 8 times 8 is 64. So that's what that looks like when you get it all FOILed or distributed. And so I'm going to combine the two 8x's since they're like terms. So it's x squared plus 16x plus 64. Okay, right now this equation looks pretty scary because I almost said squarey. Anyway, so the x squared, the 144, both sides have x squared, so it looks a little complicated. But whenever you have an equation with the same exact thing on both sides, you can subtract that off. Most people just cancel it, but look, this is why. You're going to subtract it to get it together anyway, and then what happens is they cancel off from both sides, and it just became a whole lot easier. So 144 equals 16x plus 64. And then this, you guys could solve all day long. Just a normal two-step equation. Subtract 64, subtract 64, and you get 80 equals 16x, and then you divide by 16, and you get x is 5. So x is 5. And that means this is 5, and this is 13. It's a 5, 12, 13 triangle, which is one of those popular Pythagorean triples. All right, so that's how you do that. You'll be doing some Pythagorean theorem in this section because of the right triangles. So look for that whenever you've got sides that you're trying to find instead of angles. Sometimes it will be a little easier, like if I gave you this was 5 and this was the one missing, then it wouldn't look quite this ugly, because we would have 5 here and we would add the 5 and the 8 to get the 13, and then it would be just normal x squared on one side and not on both sides, so it would be a little less complicated looking. All right, there's one more theorem in this section. Okay, it says if you have two different tangent segments, so remember, tangents are lines, but we can look at parts of lines. So if you have two tangent segments that are drawn from the same exterior point, then those two segments, meaning those two tangent segments, are congruent. Okay, so in this picture, we've got an exterior point right here. Exterior meaning exterior of the circle, outside the circle. So this is an exterior point. And from that exterior point, we've got a segment tangent to the circle here, and we've got a segment tangent to the circle here. So remember, that could just keep going and be a whole tangent line. We're just looking at the tangent segment. Well, what this theorem says is that whenever that happens, when you have from the same exterior point two different tangents, meaning they would have to be going to different sides of the circle, those will be congruent. This will be the same as this. Okay, let me show you why. Now, you don't have to write all this. I just want you to listen to why. You know how we learned a minute ago that if you draw a radius to a point of tangency, then you've got a right angle? Well, if I draw this radius, I've got myself a right angle. And if I draw this radius, I've got myself a right angle. And if I draw this auxiliary line, then I've got two triangles. And in a triangle, the radius, or in these triangles, because they're drawn in circles, the radius is the same in both triangles. And this line that I drew down the middle, remember reflexive property when they share a line? That's the same. So these two triangles are congruent by hypotenuse leg. So because of that first theorem, we had right angles, which made these right triangles. And then we have a hypotenuse congruent by reflexive property, a leg congruent because they're both radii. So we've got congruent triangles by hypotenuse leg, and that makes these segments congruent by CPCTC. Okay, so that was just a little kind of proof, I just didn't write it, of why this is congruent to this. It's a proof of that theorem. Okay, so now we're going to use it. They want us to find the perimeter of this quadrilateral. So we're using this rule that if you have an exterior point, and we've got 4 exterior points here. These are all points that are outside this circle. And from those points, we've got tangent segments. So let's do this one first. So from this point, we've got a tangent segment here, which is 6, and we've got a tangent segment over here, which is 6, according to that theorem, because it says from the same exterior point, tangent to a circle, they're going to be equal. And then that's happening at each of these corners. So from this exterior point, we've got a tangent and a tangent. So that one's 7, this one must be 7. And then from this exterior point, we've got a tangent of 3. And so we've got another tangent of 3. The two tangent segments are equal. And then the last one, from this exterior point, we've got tangent segments here and here. So if this one's 4, this one must be 4. And then to get the perimeter of the quadrilateral, all you have to do is add up the 4 sides. That's how you get perimeter. So the top side is 7, and this side on the right is 11, and this side on the bottom is 13, and this side over here on the left is 9. And I don't know if you remember from elementary school where they taught you to look for 10s. So see how these pair up to be 20 because we're looking for 10s. 9 and 1 is 10. And then These pair up to be 20, so this is 40. So the perimeter is 40. And that is how to do that one. Now they won't all be quadrilaterals. They might have some problems in your homework. Pretend that circle's pretty. Where it's a triangle made up of some tangent segments, and you could do that the same way. So just remember to find the perimeter of the actual shape. You add up all the sides of that shape. All right, so that is our lesson on tangents. And yeah, that's it. Y'all have a great day. Hang on to your tip chart so that we're going to add to it over the next couple lessons. All right, bye guys. Have a great day.